In this next section, we're going to define the high water line more quantitatively rather than asking the oldest person in the community to tell us the highest they've ever seen the water rise. Likely, the older community members will still be more accurate given how many assumptions we have to make. But it is important to understand all the factors that can affect flow rates and peak flow. One thing to keep in mind while modeling anything is that models will always give you an answer. This doesn't mean the answer is good or correct. One thing I was always told in school when we were doing building energy modeling was crap in equals crap out. So we'll do our best to limit assumptions and define our inputs with real data. So step one is going to be estimate the watershed area. One of the simplest and most effective ways to do this is with the Google Earth polygon draw feature on a topographic terrain map. Watersheds at higher elevations will most easily be defined by ridges and valleys. Make sure to take notes. Note qualitative characteristics about the watershed, so you can always go back to these notes. Note its ground cover and various topographic features. And then finally, take down the area of the watershed for use in calculations. And some other things you could note are if the vegetation is dense, or if there is bare sand, or coarse soil, or fine soil, or steep ridges. This information is good and will help you define your watershed. You can seek advice for defining your watershed with experts, and they'll want to see notes like this and have a reasoning behind why you chose this watershed area. Step two is to find potential storm characteristics. Most notably, this is the rainfall intensity and the accumulated precipitation. So, how many inches of rain fell over how much time? For this, you can use characteristic storm data or various climate data sites. For example, you can use a singular characteristic storm, like you might have heard of Eloise, Hurricane Eloise in Eswatini is a storm that defines a lot of our high water lines. Or you can use climate data sites that I will link below, but it is up to you to find more information and try and verify this information. And like I said, the two main things we are most interested in are the rainfall intensity, which is the inches per hour value, or the total accumulation of P, which is usually in total in a cumulative amount of inches. Step three is to choose the estimation method. To sound smart, I can rattle off a few options like the SCS peak discharge method or the kinematic wave method and the USGS regression method, but the most common methods will be the rational method or the SCS curve number method, both of which you've likely heard of, especially the rational method. The rational method is very similar to the SCS curve number method, both using a coefficient to represent the topography and land cover of the watershed to then calculate peak flow. The rational method is commonly used in small areas, less than 1 square mile or 640 acres and up to 200 square miles. First, we'll focus on the SCS curve number method, which is a function of soil type, land use, rainfall intensity, and the antecedent rainfall conditions, so previous wetness or dryness. Because we're only concerned with a 1-day maximum flow event, we will also ignore evaporation and transpiration, which is going to be evaporation of water and the plant intake of water. In the following steps, I'll split up into step A and step B, where step A is going to be following the curve number method, step B is going to follow the rational method, and we will converge again at step 6, where we actually go to calculate our depth of flow.